Now we're going to talk about kinetic energy, Ke, and one of my personal favorites, Ludwig von Boltzmann, okay, and the Boltzmann distribution for gases. So this is module 2.1.2.3. So if you remember the kinetic molecular theory of gases, one of the things we said was that these particles are moving around, and they have a certain motion, and they're constantly moving around randomly, and they have a certain velocity, okay? Well, to expand on that a little bit, they have a certain velocity, but they're not all moving at the exact same speed, okay? There's a certain average velocity, and the average is going to be directly proportional to the temperature, but just because there's an average doesn't mean that every single particle has exactly the same speed. Okay, some are moving faster, some are moving more slowly. Okay, and so Boltzmann came up with an equation to actually show what these velocities look like. Okay, and I'll show that to you here. Okay, Boltzmann figured out, and others, that the root mean square velocity of a gas is equal to the square root of 3RT over the molar mass. Okay, and so here's kind of a subtle thing. Average and root mean square are not exactly the same thing. Okay, the average is just the mean, the number that goes right in the middle. Okay, that's not exactly the same as the root mean square velocity, but it's similar. Okay, it's much easier to come up with an expression for root mean square, it turns out, than for average. And so that's why we're going to use this root mean square velocity. Okay, and so when you're using this formula, you have to be a little bit careful because the velocity is typically given in units of meters per second, but the R here that we're going to be using is 8.314 joules per mole Kelvin. Temperature has to be in Kelvin. Okay, and the molar mass is going to be in grams per mole. Okay, the problem here, of course, is that the joule has in it kilogram, not gram. So you're going to have to convert. Okay, the other problem is going to be just making sure that all the temperatures work out. Okay, and for mass here, this is also going to have to be in kilograms, not grams. Okay, so we're going to have to do some conversions. This graph here on the bottom shows the frequency as a function of velocity. Okay, and so the point here is that if you look at carbon dioxide, CO2, as an example, okay, not all of the molecules have exactly the same velocity or the same speed. Okay, and so at a relatively low temperature, you get something that looks like this blue curve, where most of them have a certain velocity, and then it kind of tails off. Okay, but as you go to higher and higher temperatures, the curve shifts a little bit. Okay, and so the maximum goes further and further to the right, meaning that at higher and higher temperatures, they acquire more and more velocity, right? They're moving faster and faster and faster. Okay, and so as the temperature increases, the average temperature and the average kinetic energy is also going to go up, and the velocity is also going to go up. Both the average, root mean square, the whole deviation, the whole distribution shifts a little bit. Okay, this formula also allows me to predict what the relationship is between temperatures and molar masses and velocities. Okay, and so generally speaking, as temperature increases, the root mean square velocity also increases, because you can see that the temperature is in the numerator, or it's directly proportional to that. But it's directly proportional to the square root of the temperature, right? So if I want the thing to go twice as fast, I have to increase the temperature by a factor of 4. Okay, now if I look at the molar mass, which is on the bottom, as the molar mass increases, the root mean square velocity actually decreases. Okay, that also makes sense, right? As things get heavier, they move more slowly. It's harder for them to get around. Okay, and so the velocity is going to decrease as the molar mass increases. But once again, it's only going to be inversely proportional to the square root of the molar mass, not the molar mass itself. So something that's 4 times heavier is going to move half as fast.